Alright everybody, what is going on? This video we are looking at vector functions and space curves. So let's go ahead and get started. So if we have f of t, g of t, and h of t are components of the vector r of t, then f, g, and h are real valued functions called the component functions of vector r, and we can write that the vector function r is equal to f of t, g of t, h of t. And we can also write it as f of t times vector I plus g of t times vector j plus h of t times vector k, and t is the independent variable. And remember vector I is the vector 1, 0, 0, j is the vector 0, 1, 0, and vector k is the vector 0, 0, 1. All right. So, it's like a vector, except instead of having numbers there, like vector 1, 2, 3 or vector -2, 5, 3. The components are these functions f of t, g of t, and h of t. All right, so let's look at this. We're gonna find, as you can see in this example, the domain. We're gonna find limits, and we're gonna do some graphing. So stick around and watch the whole video and see if you learn something. All right, so find the domain of r of t is equal to t cubed, natural log of 3 minus t, and square root of t. So remember, this right here, this f of t, g of t, h of t, it's like this is your x, y, and z. Okay? And so when we work this, we can actually write x is equal to this first function here, this t cubed. We got y is equal to natural log of 3 minus t, and z is equal to square root of t. And yeah, if you wanted to, you could write f of t, g of t, h of t. Okay, same thing. All right, so we need the domain of this vector function here. So we look at each one of the components here, and I don't know if I said limit. If I said limit, I meant domain. If I said domain, then it's domain. All right, so we need the domain of this first function here. Well, what's the domain of t cubed? Well, you know that for that one, that t can be anything. It can be between negative infinity and positive infinity. Now, let's just skip over here to this one. We'll come to this one last. Let's look at this one. What about square roots? Well, we know we can only take the square root of a positive number. So t has to be greater than 0. But let me ask you this. Can t equal 0? Yeah, we can take the square root of 0. So t has to be greater than or equal to 0. And then what about logarithms? Can we take the log of a positive number? Well, of course we can. Can we take the log of a negative number? No, we can't take the log of a negative number. If you have your calculator sitting by you, type in natural log of -2 and see what it gives you. It'll give you an error message. Now, what about taking the log of 0? Well, we can't do that either. And you can punch in natural log of 0 into your calculator. It'll give you an error message. So this 3 minus t here has to be positive. And so if we take the minus t, move it over here, we get t is less than 3. So t has to be less than 3. Now, the domain, it has the numbers that we plug in. You don't look at it as satisfying each one individually. It has to satisfy all of them. So yes, for this one, t can be anything. But over here, it has to be greater than or equal to 0. And here it has to be less than 3. Okay? All right. So everything that's negative is out. Okay? We can't use any negative numbers for t. Okay? Because for this one, it says it has to be greater than or equal to 0. All right? And then if we move in the positive direction, and of course we'll have a bracket here because the 0 is included, and it says that t has to be less than 3, so that means we can go all the way back. See, look at this. Here's the 3. Here's 0. It has to be less than 3, so that means it has to go all the way back this way. You see that? But we have to cut it off right here because of this one. So it's going to be from 0 to 3, but the 3 is not included because this cannot, because if we plug 3 in, we would be taking the log of 0. And so we'll put a 3 there, a parenthesis there, so the domain is 0 to 3. All right? So you just got to look at all of them, and it has to be where it satisfies every single one of them. Yeah, negative infinity to infinity on this one. So this one, it can be anything. But then we've got to go to the ones that are a little more strict on what the domain should be. Okay, so it's got to satisfy every single one of them. All right, so let's look. All right, I don't know what happened after I worked that first example and started talking about limits and continuity. My screen started acting like it was coming detached. I have a Surface Book 2, and it just stopped the recording. So I saved that part, and now I'm continuing. So let's go ahead and get started back again. All right, so limits and continuity. So if the vector function r is equal to f of t, g of t, h of t, then the limit of r is equal to, well, look at this. All you do, you take the limit of each component individually, provided the limits of the component functions exist. A vector function r is continuous at a if the limit of r of t as t goes to a is equal to r of a. Okay, and that's similar when you were doing limit continuity with functions. Okay, if a function was continuous, you took the limit of the function as x approached a, and that had to equal f of a. Okay, same thing here. All right, so let's look at an example. And so we have find the limit of r of t as t goes to 0, where r of t is equal to this thing. So all we're going to do is we have the limit as t goes to 0 of r of t is equal to, all right, that's equal to the limit as t goes to 0 of 1 plus t cubed times vector I plus the limit as t goes to 0 of t e to the negative t times vector j plus the limit as t goes to 0 of sine t over t times vector k. So all I did is I took the limit of each one. Okay? That's all we're doing, taking the limit of each of those components. So let's just come down here and do the limit as t goes to 0 of 1 plus t cubed. And yes, I understand you can do this in your head, but I'm going to write it out so you can see it. So let's do the limit of this one. So here, well, we just plug the 0 in and we get 1. And then we have the limit as t goes to 0 of t e to the negative t. Well, that's the limit as t goes to 0 of t over e to the t. And for this one, I mean, we can just plug the 0 in. E to the 0, which is 0 over 1, which equals 0. And then we have the limit as t goes to 0 of sine t over t. Well, when we plug the 0 in, we get what? We get 0 over 0. So we can do what? We can use L'Hopital's rule. So we just take the derivative of each of the numerator, derivative of the denominator. And so this is going to be cosine 0, which is 1. So we get this is 1, this is 0, and this is 1. So we have the limit as t goes to 0 of r of t is equal to, well, this is 1, so 1 times vector I, that's I. This is 0, so this whole term is gone. And then plus, and then this is 1, so 1 times vector k, that is just k. And so this is our limit. All right, so that's not too bad. That just kind of going back to just basically taking limits is all you're doing. All right, so let's look at this. Suppose that f, g, and h are continuous real-valued functions on an interval I, then the set C of all points x, y, z in space, where x equals f of t, y equals g of t, and z equals h of t, and t varies throughout the interval I, is called a space curve. The above equations are called parametric equations of C, and t is called a parameter. And you know, I was talking about this earlier, where we refer to these to the functions f of t, g of t, and h of t as x, y, and z. Okay, and you have what? Parametric equations. Okay. All right, so let's look at this. So describe the curve defined by the vector function r of t is equal to 1 plus 2t, 2 plus 5t, and negative 1 plus 6t. All right, so just says describe the curve. So let's talk about the curve and maybe even draw a graph of it. So we have x equals 1 plus t, y is equal to 2 plus 5t, and z is equal to negative 1 plus 6t. And what in the world is this? Okay. Well, if you refer back to earlier sections, and I'm not gonna state the section number, but it's the section, because you know not everybody's using the same book as I'm using. But it's the section on lines and planes. And hopefully you recognize this as being a line. That's all this is a line. All right? And do you remember at t equal 0, we have the point what? What's a point on this line? A point on the line, remember 1, 2, negative 1. 1, 2, negative 1. All right. And what else do we know about this? Well, we also know that it's parallel to the vector, we'll call it vector v, 1, 5, 6. See? The 1 is the coefficient of this t, the 5, and then the 6. It's parallel to that vector. And hopefully that's bringing back some memories. All right, so we've got a line. Let's get 2 points. Okay, let's get another point on here. Okay, and you know, for t we could plug in, you know, pretty much anything we wanted. And you know something, I think I copied this problem down wrong. All right, so you see this 2 here. I don't want that 2 to be there. I want it to just be 1 plus t. Okay. All right. And that's where this 1 plus t comes from. So if that was confusing you, I didn't mean for that to be a 2. All right. All right, so now let's get another point on the line, and let's just choose t equals -1. So why am I doing that? Well, you can plug in whatever you want, but why would you do that? I mean, you can plug in 10 if you want to, but then you got to plot the point 11, 52, and then 59. If you chose 10, you don't want to do that. I chose -1 because it's going to zero this one out, and then I just got to worry about plotting these 2 points right here. Okay, and if you wanted to, you could pick something that makes this one 0 or this one 0, but then you would be picking fractions. So just choose t equals -1. So if we choose t equals -1, that's going to give us a point. We'll just call it Q. So we know we're going to get 0 here, and then if we take the -1 and plug it into here, that's going to give us -3. And then if we plug the -1 into here, that's going to be -1 plus -6 is -7. And so there's our 2 points right there. So let's sketch this line. Okay. So let's see. Let's do this. Whoop, let me draw that better. Here, here, and there's Z. And there's X, Y, Z. And let's go ahead and bring this down. That'll be good enough. And let's bring this on across, because we got to plot some negative values there. All right, so we've got, let's see, 1, 2, 3, 4. And then we've got 1, 2, 3, 4. And then we got 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7. All right, so let's start out with that. Oh, we need to go over here too. 1, 2, 3. All right, so let's plot the point 1, 2, -1. So I'm going to come over 1, and then going to go over 2, which is here, and you can see those are going to meet right here. Okay, and then we have Z is -1. Okay, so if we look at this right here, and -1, that's going to be right here. So that point's going to be about right here. There's that point on the graph. All right, and then we got to plot the point 0, -3, -7. So here's X is 0, Y is -3, and then I need to go down 7. So we're going to come down here to about right in here. So there's this point. We'll call this point 0, -3, -7, and this is the point 1, 2, -1. And then we draw our line. And that's what that line's going to look like, something like that. And we can draw the x-axis coming on out like that. But yeah, here's your line right here. Okay, and so that's what you've got. Recognize that that's the equation of a line. You got your parametric equations. Refer back to that section on lines and planes. There's a section on this. Okay. And then the other thing that I want to mention here, plane curves can also be represented in vector notation. So let's suppose we have the parametric equations x equals t squared minus 2t and y equals t plus 1. Then we have r of t is equal to, and so that would be what? T squared minus 2t and t plus 1. All right, which is equal to, and we can write this as what did I write? T squared minus 2t, and that's times vector I plus, and then we've got t plus 1 times vector j. Now notice here all we have a x and a y. We don't have that z component, do we? So here vector I would be the vector what? 1, 0, 1, 0, and vector j would be the vector 0, 1. Okay, so you can represent plane curves as in vector notation. Okay. All right. So let's take a look at this example. Sketch the curve whose vector equation is r of t is cosine t I plus sine t j plus t k. All right. So when we're graphing these vector functions, where it's going to be a curve, it's a space curve, and what it's doing is the space curve is going along some surface. Okay, so what we'll do first is we'll need to graph the surface. Okay, and then we can graph our vector function. We can graph our curve, our space curve, and the space curve, like I said, is going along the surface. So let's work the example, and I'll explain more as I'm working through the example. So we've got x is equal to cosine t, y is equal to sine t, and z is equal to t. So the first thing we want to do is graph the surface. Okay, let's graph the surface. Now, to graph the surface, you want to, I mean, there's different ways you can do it, but look, take two components that you know. Okay, like this x equal cosine, y equals sine. Well, what do we know about that? We know that cosine squared plus sine squared is equal to 1. Okay? So that tells us that x squared plus y squared is 1, right? Cosine is x, sine is y. So we've got x squared plus y squared equals 1. That's given us the projection in the xy plane, right? So if we go to graph this thing, maybe not. All right, so I've got x, y, and z. So the projection in the xy plane, what is that? Well, let's go ahead and let's draw a positive and negative. I'll do them with dotted lines. And so we know this is just a circle with radius 1, right? So it's going to look something like this, right? And then as we move up, see, as the values of z change, it's just going to be circles going up the z-axis. So we know here we have a cylinder, don't we? You see that? And then what we're going to do is we will pick some points for t and plot those points. And look what's happening. This is the surface that your space curve's going on. So when we pick our points, okay, so, and let's just pick one. So for instance, t equals 0. So I'm going to take this t equals 0 and I'm going to plug it in here, and that's going to give me the terminal point of the vector. Okay, so if I plug the 0 in, cosine of 0 is 1, sine of 0 is 0, and then plug 0 in for t, I get 0. So what this is This is the terminal point of the vector going from the origin 0, 0, 0 out to the point 1, 0. So, and then what I would do is I would pick another value of t. Let me just do that real quick, and then I'll explain something about what's going on. So I can pick any value I want for t, right? I can choose any value I want. It doesn't matter what value I choose for t. So look at this. We've got, I guess I need to pick a value first. I'm going to choose pi over 2. Why? Well, because I know the cosine and sine of pi over 2, and it's going to give me what? I'm going to get values like 0, 1, -1, right? And I'm graphing this from 0 to 2 pi. So the values I would choose, yeah, I can choose pi over 3. I can choose pi over 6. I could choose 5.79 radians if I wanted to, but why? Why would you do that? Okay? All right. So now if I choose the pi over 2, the cosine of pi over 2 is 0, the sine of pi over 2 is 1, and then I plug the pi over 2 in for t right here, and that's going to give me pi over 2. All right, and then we can go with t equals pi. And so if I plug in pi, I'm going to get what? -1, 0, pi, right? The cosine of pi is -1, the sine of pi is 0, and then plug the pi in for t. And I could plug in 3 pi over 2, and let's just go to 2 pi. I think this will be enough to give us an idea of what it looks like. So the cosine of 2 pi is 1, the sine of 2 pi is 0, and then plug the 2 pi in for t right here. All right, so what's happening is, let's plot this point, 0, 1, pi over 2. Okay, all right, so 0, 1, that's going to be here. See, x is 0, y is 1, and then I'm going to go up pi over 2, which is about right there. So what's happening here, and let me do this. So you see it's a vector here. There's a vector here. And what's happening is it's going to be vectors just hitting on this cylinder. You see that? These vectors is just going out. Now, keep in mind, this vector it's like going to the back of that cylinder there. And it's just, you're picking these points, and these vectors are going from the origin here, and they're just going, when you calculate these terminal points, they're going and they're hitting on that cylinder. And that curve is being traced on the surface of that cylinder. Okay? All right, so let me get rid of those vectors there, so it's not so cluttered up. But yeah, I just wanted you to see that. Okay. All right, now let's plot the point -1. So -1 right here, and then 0, pi, 0. So the y would be 0, and then we're going to go up pi units, which I guess is maybe about right in here right in here somewhere. And then we've got the point 1, 1, 0, 2 pi. So that's going to be maybe somewhere up there like that. And so when I draw this, it's coming around like this. Okay? It's coming around like this. And it's, let's see. All right, so like I've mentioned in past videos, I'm not the best at drawing these things. So it's going to come something like this, and then it's going to hook back around. See, it's just following these points. Well, let's see. Maybe something like this. and it's going up. It's going around the surface of that cylinder. It's going up, and this is what? This is a helix. Okay, and it's going up that cylinder. Now, you see how the t values are going, and we need to put arrows on there so we know which direction. And look, you can see we're moving this way, right? So we're moving along like this. Okay. And of course this thing, it just keeps going. But yeah, it's, it can be kind of difficult to draw these things, but it's not too bad. But there's the graph of it. So just take your time and just take two of the components and see if you can get that. See if you can see what's going on there. All right. You want to take two of the components, get that projection in the XY plane, if you can, and then then draw your cylinder, and then get some points, or it might be where you recognize what the graph looks like, and then you can draw the curve on the surface. All right, so let's look at this one, and I believe this is the last example. All right, so we've got, well, no, it's not the last example. We got a couple more to do. So find a vector equation and parametric equations for the line segment that joins the point 1, 3, -2 and 2, -1, 3. All right, so let's look at this. So if you recall back from the earlier sections, I think it was might have been the section on lines and planes, I think. Yeah, it's the section on lines and planes. And remember, all right, so what do they want? A vector equation and parametric equations. So remember, let's go ahead and get the vector equation. So remember, you had a property there that said R of t is equal to 1 minus t times vector R0 plus t times vector R1. Okay. And we have 0 less than or equal to t less than or equal to 1. Okay. If you can go back to that section and look at that property. All right. So let's find the vector equation. Well, we have vector R0 is equal to what? 1, 3, -2. There's your R0. And then, R1 is equal to this one. That 2, -1, 3. And so guess what you do now? Now you just plug it in, don't you? So you've got vector R of t is equal to 1 minus t times vector 1, 3, -2 plus t times vector 2, -1, 3. And then we can just multiply all this out, and we get, what do we get? We get vector 1 minus t, 3 minus 3t, what is that? 2 plus, let's see, wait a minute. -2 plus 2t. Okay, so all I did, I took the 1 times this, I took the 3 times this, and then the -2 times that. All right, and then that's plus, and then I'm going to distribute that t, so that's 2t minus t plus 3t. I'm sorry, 3t, not plus. And then all we're going to do now is just add these vectors together. So I've got 1 minus t plus 2t. So I'm multiplying the first components together. So I get RT is equal to, that's going to be 1 plus t. See, negative t plus 2t is t. And then add this one and this one. So that's going to be 3. And then negative 3t minus t is minus 4t. And then negative 2. And then 2t plus 3t is 5t. And there's your vector equation. And now they want the parametric equations. Well, that's easy. So we've got x is equal to 1 plus t, y is equal to 3 minus 4t, and z is negative 2 plus 5t. And there you have that. So this is the vector equation, and this is your parametric equations. All right. Okay, and so the next thing I want to show you about this. So you in this problem you saw how we found our vector equation. We used this right here. So you might remember this one, and let me do it in a different shade. You might remember that R of t is equal to R naught plus vector vt, where v is the vector. Well, our line is parallel to this vector v. Remember that? Okay, this was another way to get the equation. So we've got right here, we've got R naught. I mean, and look, you can find the equation either way. You can do this or you can do what I'm doing here. Okay, so we got R naught is this 1, 3, 2. Okay, that's your 1, 3, negative 2. And vector v, what is that? That is parallel to that vector. That we need the direction of it. So remember, it's this point minus this point. So it's going to be 2 minus 1, negative 1 minus 3, and 3 minus negative 2. See that? I just did this minus this, this minus this, this minus this. And so I get v is equal to 1, negative 4, 5. And so now we just plug that into here. Okay? And so that's going to give me R of t is equal to what? 1, 3, negative 2 plus vector v, which is 1, negative 4, 5, and times t. I don't think I've gone off the screen. Okay? And so now we just distribute that t, and so that's going to be R of t is equal to, all right, so let's look at this. So I'm going to distribute the t. So that's going to be 1t. 1 plus 1t is 1 plus t. Distribute the t, that's negative 4t. 3 plus negative 4t is 3 minus 4t. And then we distribute the t, that's 5t. Negative 2 plus 5t is negative 2 plus 5t. And there you have it. Okay, and you can see it's the same thing as this. All right. All right, so this is our this is our last problem right here. So it says find a vector function that represents the curve of intersection of the cylinder x squared plus y squared equals 1 and the plane y plus z equals 2. All right, so what I'm going to do here, I'm gonna sketch this real quick, and then I'm going to erase the sketch and kind of draw it again to make it look a little better. This one, I mean, for me, it's kind of, this one's difficult to draw, but anyway, let's just look at it. You know, and that might be something you want to do on some of them. I don't know, just kind of sketch it out and then draw it again and make, you know, to make it look better. So there's your x, y, and z. All right, so, well, we know this is x squared plus y squared equals 1. So there we have our cylinder here, or our circle there in the xy plane, and this is a cylinder. All right, so we've got this. All right, now the plane y plus z equals 2. Okay, so this plane here, it's gonna be slanted. You know, it's gonna be kind of like, you know, coming this way. Okay, you can see. I mean, I guess you could say when y is 0, z is 2. Okay, you're about right here, and then, you know, the x values are whatever. You know, it goes in both directions. So the plane's gonna, you know, kind of go like this in both directions. But you can see when y is 0, z is 2, and when z is 0, y is 2. So I mean, I guess you can kind of see it, that it's gonna be slanted like this. It's gonna be a plane. It's gonna go through here, and like I said, I didn't draw this good. Let me see if I can make it look a little bit better. You know, something like this. You know, something like this, and it's going to intersect that curve. But understand that this thing, it's kind of slanting like this way. Okay. So like I said, let me erase this and maybe draw a little bit better picture. But this is just a rough sketch of it right here. So, you know, by all means, do a rough sketch like this, and then say, okay, well, let me see if I can do a little bit better job of drawing it. I mean, and like I said, you might be better than I am at drawing these things, but, you know. But basically what we have here is we've got this cylinder coming down like this, and it's coming up like this. That's the cylinder. We've got here, and we've got this plane coming like this. It's coming here, and then it's coming here like this, and it's coming this way, and let's say right here, maybe something like this, and then we've got, let me maybe not come down so far. Whoop. It's coming maybe something like this. Just bear with me. And so then and then the bottom of the cylinder's coming out like this, and maybe right here, and there's that cylinder, and you can see the planes kind of going through that cylinder there at an angle. And then you would, you know, you have your x-axis coming out here like this, your y-axis like this, and then of course you've got your z-axis coming here. And what we have here is this intersection right here is what we're looking at, okay? And it's going around, and it's coming back through like this, okay? So you know you're kind of looking at this thing right here, this part right here. And so if I come over here and look at it, well, let's maybe kind of make it look like this X, Y, and Z axis here. So you got X, Y, and you've got Z. And so it's kind of like this right here. It's elliptical there, and it's at a slant, okay? And you can see here, you know, if we bring this down, okay, it's a circle. Its projection. Its projection is a circle in the XY plane if you project it down. And so maybe let's get a, we can maybe get a few points on it. Let's see what that does. And so if we have y equals 0, okay, so if we have y equals 0, then that gives us x squared is equal to 1, which means x equals plus or minus 1. So I took the y equals 0 and plugged it into there. And then if I plug the y equals 0 there, I get z equals 2. Okay? So that gives me the point plus or minus 1, that's x, and then it's actually 2 points, and then I get y is 0 and z is 2. So I've got the point 1, 0, 2 and negative 1, 0, 2. And so if I plot that, that's going to be like this point and this point right here. This is negative 1, 0, 2, and this is the point 1, 0, 2. And then I can say, okay, well, what about when x is 0? Okay, well, when x is 0, that's going to give me y squared is 1. So that's y squared equals 1, which means y is equal to plus or minus 1. And z would be what? Well, there's going to be 2 things that happen here. Let me write these equations right here. I've got x squared plus y squared equals 1, and y plus z equals 2, just so we can see them. All right, so that's going to give me, when y is 1, that's going to be 1 plus z equals 2, so that means z is equal to 1. And then I'm going to have y is negative 1 plus z equals 2, so z equals 3. So that's going to give me the points 0, 1, 1, and the point 0, negative 1, 3. See, from this, x is 0 in both of them, and then y is 1, z is 1, y is negative 1, z is 3. And so that's going to be like this point here and this point here. This is going to be the point 0, 1, 1, and this is going to be the point 0, negative 1, 3. And so, that's what you have there. And so we know we have our projection on the XY plane is what? It's a circle, right? See, you can see this is a circle. See, look. See, we go this way 1, we go this way 1, and we're back. When y is negative 1, and then we've got a 1 here. You see that? The 1. See, it's a distance of 1 along the x and y axis. And so we have a circle, Okay. And so, well, what do we know? Well, it's a circle, so we have that is actually what x squared plus y squared equals 1. But that tells us that x is, we know x is equal to cosine t, y is equal to sine t. All right. And then what do we have? Because remember, you know, we did something up here. Where is it? Right here. You know, see, we had the cosine t, sine t. That was our circle there in the xy plane. Remember that? All right. So now, what do we have? We've got x, we've got y, but now we need what? We need z. Well, what is z? Well, look at this. We have y plus z is equal to 2, right? That was one of the equations they gave us. And so z is equal to what? 2 minus y. So z is what? 2 minus y, which is sine t. And so we get z is equal to 2 minus sine t. So this is our parametric equations. Let's write our vector equation. So we got vector r of t is equal to cosine t I plus sine t j plus 2 minus sine t k. And we are between 0 and 2 pi. All right, so, you know, I know that these things, it's really not, it's not hard to do the math part of it. Probably the more difficult thing that you're going to be doing is just trying to graph these things. And I don't think it's so much that they're difficult to graph. You know, it's not that they're difficult to graph. You know, as far as how to graph it, as far, you know, it's not difficult for me to graph the things. The hardest part to me is making it look decent to graph. Okay, because I'm terrible at drawing. And you've probably seen that in the videos that I've done on all this stuff. But, you know, that's the video. I hope it helped. Check out my other videos. Give me a like, share, and subscribe. Thanks for watching. And I'll see y'all in the next one. Later.